Happy to be here today to host this webinar on V2X interoperability at scale. We're going to be focusing on connected intersections, and we pulled together an amazing panel for you to learn about what's happening with connected vehicles and connected intersections right now. As you mentioned, I'm a senior VP with WSP, serving as our national ITS lead. I have more than 20 years experience working in the transportation sector and a little more than a decade working on advancing connected vehicle and V2X solutions. I'm currently co-chairing the ITS America community of practice that's focusing on workforce development, and I'm also heavily involved with TRB and WTS. We also have Frank Perry with WSP. Frank has over 30 years of program management, systems engineering experience, and 20 years of deploying, integrating, testing, and operating connected vehicle systems. He's been part of the SAE V2X standards development since 2004 and is executive member on the OmniAir Consortium Board of Directors. Lauren Cordova is the head of technology at Cirrus by Panasonic, with 20 years of experience developing technologies for NASA, medical, defense, energy, and transportation solutions as a mechanical systems and data engineer. Kale Lindstedt heads Cirrus by Panasonic in the sales and product strategy functions, bringing more than 10 years of experience leading teams to develop complex transportation solutions across government, startups, and Fortune 500s. And last but not least, Blaine Leonard with Utah Department of Transportation is the transportation technology engineer. He's based out of Salt Lake City, Utah. And in his current role, he leads the planning and deployment of connected and automated vehicles and related traffic management technologies. His team is on the forefront of operational connected vehicle deployments. All right, and with that, I'm just going to get into an overview. Hold on one second. My slides are not advancing. Hold on just one second. Okay. Sorry, guys. All right, so this is our overview for today. There we go. Give a brief background on interoperable connectivity. Then Frank Perry will talk about connected intersections program validation and testing that has been going on, along with an update about the connected intersection message monitoring system. Then we'll hand it over to Lauren and Kale to talk about what Cirrus is doing to support the connected intersection message monitoring system. And then last, Blaine will give an update about what's happening with the Utah DOT experience with these technologies. Please use the Q&A pod to enter any questions throughout the webinar. Questions will be answered at the end of the webinar or via email like afterwards. So just to kick things off, there's been a lot of momentum to support connected vehicle and V2X deployments. Both public and private sector partners are eager to see these technologies deployed, active, and deployed at scale. There has been industry consensus on the 5.9 spectrum allocation. A couple years ago, we saw that spectrum shrunk, but we're still continuing to use it. And it's imperative to demonstrate the effective use of the remaining spectrum to the FCC and to other industry partners. USDOT has been very active in this space. They've held several connected vehicle summits, and the information from those summits is really great. It's posted on their website. The first one was back in 2022. Then in 2023, they held 2 different summits, and we expect there to be another one in 2024. There's also been numerous grant opportunities that have come up through USDOT, such as the latest one that came out last fall and was due earlier this year, which has not been awarded yet. But it's also been part of the other grants that have come through the bill and different things. So SMART was another one that really clearly specified V2X deployments, as well as ATTAIN and others as well. Also, USDOT has put out the draft document this titled Saving Lives with Connectivity. It's a plan to accelerate V2X deployment. So this is their deployment plan. Hopefully you've had a chance to provide comments on this, but it really provides this integrated technology and a connection to the Vision Zero approach, and really requires this interoperable connectivity. So how do you do that? It's through the connected V2X technology that has to be reliable and has to be seamless across communities in order to really be effective at scale, which is the point of what we're talking about today. And then it has short-term deployment plans, which includes infrastructure deployments, vehicles, spectrum and interoperability requirements, and then also different benefits and technical assistance that can be available to help with these deployments. Hand in hand with that, ITS America came out with their national V2X deployment plan with some short-term goals for different size communities, and really looking at what features and capabilities are going to be required to have full-scale deployment across the country. Now I'm going to hand it over to Frank Perry to talk about some of the things that he's been involved with working with WSP. Frank?
Thanks, Virginia. So good day, everybody. Going to be providing an overview of a couple of projects that WSP and others have been involved in an attempt to assess interoperability. Next slide, Virginia. So, but before I really get started, wanted to touch on a few common terms and definitions. So a connected vehicle system is composed of several components. One is a roadside unit that broadcasts infrastructure data to vehicles and other mobile devices. The onboard units, which are in the vehicles running the applications based on the data that is broadcast by the infrastructure and other vehicles. And then supporting systems like signal traffic controllers that provide data to the RFUs to broadcast. So we're going to be talking about 3 specific V2X or connected vehicle messages. So the first one is the signal phase and timing or STAT message that's broadcast by the RSU. So it contains signal timing information for the intersection in which it's installed. The map message, also broadcast by the RSU, contains the intersection geometry. And then finally, we have the basic safety message that's broadcast by vehicles that contain vehicle situation data, such as its location, speed, and heading. And all of these messages and others support both vehicle-to-vehicle safety messages or safety applications, and vehicle-to-infrastructure safety and mobility applications. And also security is a big component of any connected vehicle system, as devices have to be able to rely on the data that they're receiving. So next slide. So why is interoperability important? So realizing the safety benefits of a connected vehicle system requires the vehicles to receive and process data from the infrastructure as well as other vehicles. So obviously, deployment of connected vehicle devices in production vehicles is critical to the entire system. However, vehicle manufacturers require consistency and reliability in the data so they can provide dependable and reliable user experiences. I also want to highlight here that the USDOT has a Smart Community Resource Center that has an entire section of interoperable connectivity. So next slide. So some of the challenges of interoperability. So interoperability is more than just an overarching principle. There are specific items that must be accounted for. For example, the messages and the data exchange between the devices, interpretation of the data, and this is really critical, interpretation of the data that's contained in the messages. And then trust and security. So again, devices need to be able to trust the data that they're receiving from the infrastructure. Now, previous deployments primarily focused on ensuring that messages and data were compliant with SAE J2735, which is the CV data message set dictionary, but it's been proven that is not enough. Also, deployments or applications tend to be deployment specific, meaning messages only contain the data that's needed to support their particular applications. So if you take a vehicle application from one deployment, it may not work in another deployment. So next slide. So this is where another standard comes in, the Connected Intersection Implementation Guide, CTI 4501. Right, so this document contains a consensus between agencies, between automotive manufacturers, connected vehicle device manufacturers, traffic signal controller manufacturers, and developers around what is required for interoperability. The initial ITE released the initial document back in September of 2021, along with an update in June of 2022. Now, SAE is set to release version 2 of that document in the fall of 2024. Thanks. Slide 11. So, really, when we talk about interoperability, how interoperable are existing deployments? So the Connected Vehicle Pool Fund Study initiated a project in early 2022 to assess connected vehicle system interoperability between its members based on 4501. A total of 15 intersections were tested across 3 states. Next slide. So here's the Connected Intersection Program team. So all the Connected Vehicle Pool Fund Study members are along the top. WSP and Athy Creek were the consultant team, and sites were tested in Utah, Georgia, and Ohio. Next slide. The testing consisted of three areas. So the first one is you wanted to make sure that the SPATA map messages contain the data required in 4501. And then we documented the communication range of each of the RSUs. And then we assessed the latency between when the traffic signal had changed and when that change was reflected in the SPAT message. Next slide, please. So all in all, well, we tested 128 requirements, and the states gained valuable understanding of the system performance and the message interoperability. There was some consistency across all the states, and there were also areas that needed improvement. So, in fact, WSP is wrapping up its second round of testing based on updates that each of the 3 sites did as a result of our initial round of testing. So, next slide. So, validation is required to ensure connected intersections operate as intended upon initial deployment. However, what happens after deployment? This isn't a set it and forget it and everything works fine forever. Things change. Roadway geometry changes, signal timing plans change, devices have the software and firmware updates applied. It's not so running this initial validation process at every intersection, every time something changes, is simply not scalable. However, what if we could automate some of this testing and continuously monitor these intersections after deployment? Next slide. That's kind of where the Connected Intersection Message Monitoring System comes in. Its objective is to continuously monitor connected vehicle messages broadcast by each intersection and identify when the messages no longer match the roadway environment. And when those when the messages no longer match the roadway environment, we notify the system operator so that corrective action can be taken in a prompt and efficient manner. So CIMMS monitors SPATAMAT messages and assesses how well those messages align with driver behavior based on the basic safety message. So next slide. So again, here's our project team, pooled fund study members across the top. WSP and NERA Consulting is the consulting team, and the prototype was deployed at 3 sites in Utah and 3 sites in Maricopa County, Arizona. And Utah was supported by Panasonic, who obviously we'll hear from in a few minutes, as well as the Narwhal Group. And then Maricopa County was supported by University of Arizona. So next slide. So CIMMS was designed with simplicity in mind. And here we're talking a single connection to the roadside unit and providing data, and then a graphical user interface that enables system operators to view details of the intersections that they're monitoring. Next slide. So this slide shows the relationship between the algorithms of the SIM, basically the processes that the SIM contain, along with the 3 messages that it is ingesting. So SIMS evaluate SPATAMAT messages independently, meaning, do those messages contain all the required data elements, again, per 4501, and it also ensures that that relevant data is the same in both messages. So like make sure both SPATAMAP have the same intersection ID, have the same signal groups, et cetera. And then also it evaluates how well the SPATAMAP messages represent the roadway environment by using the BSMs to gauge driver behavior. So one thing I want to mention here is, assessing driver behavior takes multiple vehicle passes. For example, the SIMS is not going to notify the operator of a potential issue if a single vehicle appears to be making an undefined maneuver. So next slide. So WSP conducted some control testing in Maricopa County to ensure the system could identify and capture specific events, such as when vehicles cross the stop line, and ensuring that the vehicle direction of travel matched the direction of travel in the map messages. All in all, the prototype demonstrated that messages can be continuously monitored and provide valuable feedback to the system operator, and that CIMMS is scalable, meaning we can add additional RSUs to be monitored with minimal effort, and that the visualization component is very useful. In fact, visualization really received most of the feedback from the users. We're getting phone calls and emails quite a bit saying, "Hey, it'd be great if the system showed this, or if I could, or if I could look at the intersection from this perspective, or whatever." So the visualization was a big hit with this system. Also, using BSMs showed that the BSMs are good for some evaluations, but it does have its limitations. For example, BSMs work great for determining the direction of travel, both on the vehicle and then comparing that to the map message, but it's not so good really at identifying the center line of the lane, which is relevant for some things. Really the BSMs are only as good as their positional accuracy. All of the CIMMS is open source, so others can download it and deploy it if you wish. And then next slide. So robust initial validation verifies that the CV infrastructure adheres to its established standards and and promotes interoperability between jurisdictions. So here we can take a vehicle from one deployment and have it operate or correctly in another deployment. So initial validation is critical. However, we still need this continuously monitoring portion, to identify issues or inconsistencies and errors as they pop up. So as I mentioned, once the system's deployed, maybe there's a lane geometry change at the intersection. Well, somebody may not realize that they needed to update the map message, but the CIMMS in this example would alert that immediately as vehicles may be traveling or going through the intersection different than how the map message is laid out. And continuously monitoring the system really enhances the overall reliability of the system. And with that, Virginia, I will hand it back to you.
Great. Thanks, Frank, for that presentation. Super interesting to hear about all the work that you've done with the Connected Vehicle Pooled Funds study and, advancing the connected intersections and the CIMMS product. All right. Now, next up, we have Lauren and Caleb from Panasonic. Hand it over to you.
Yeah, thanks, Virginia. Hopefully everybody can hear me okay. Appreciate the opportunity. So I think Frank did a nice job of setting up some of the really amazing work that WSP has done, developing the concepts behind the CIMMS tool and how that work is supporting connected intersections at scale. You're going to hear shortly from Blaine, who's going to talk a little bit about, excuse me, how Utah's experience with some of these tools has been and what they're doing with the infrastructure. And I want to fill in between with a little bit about what Panasonic is doing to try to bridge between those two things. And so, as Frank mentioned in a couple of his last slides, some of the work that they've done, it's open source, it's proof of concept. They've done a ton of research that's built this. And what we're doing at Panasonic now is adding these tools actually into our connected vehicle product so that we can take it out to our DOT customers and help to support this concept at scale. So I'm going to go to the next slide, Virginia. Awesome. So Cirrus by Panasonic is based in the cloud. It's a platform for connecting sort of all the different dots of a connected vehicle deployment. And I'm going to talk just a little bit about what that means at a high level, and then I'll hand it off to Lauren, who will get a little bit deeper into the architecture so you can see how we're adapting some of these functionalities to meet this connected intersection at scale, and particularly the CIMMS logic at scale and some of the deployments that we support. So I'll run through this slide just briefly. At the bottom layer here, we have the hardware that's out in the world, and that might be vehicle side, it might be an OBU. We do some things with other kinds of connected devices that we pulled data in from. It might be the DOT infrastructure, so connected intersections, the roadside units that support V2X, and some of the other stuff that they're connected to, switches, traffic signals, et cetera. All of those devices have information to tell us about what's happening out in the real world. And we use Cirrus as a way of aggregating that information and putting it into a place that's this middle layer where we can store and analyze that data. So we're getting things like BSMs and SRMs, we're getting SPAT data off traffic signals, we're getting non-V2X, position data from other types of endpoint hardware. All of that feeds into what's called a data warehouse or a data lake through a relatively standard device interface. So we can connect different kinds of devices to different levels of infrastructure or on the vehicles out on the roadway. We can get the information into the system that they have to share with us about either what they're doing as a road user or what's happening around them in the infrastructure. And then once we have that data, we have some techniques for how we store, process, analyze, and clean that up. And then we connect that to a really modular front-end system that lets us plug in different kinds of applications depending on the particular use case or the particular customer. And so this gets to how we're attaching kind of the CIMMS logic that WSP has developed into this ecosystem that we're supporting with Utah and other DOTs. I'll show a couple of examples of some of our actual product screens after I give Lauren a chance to talk a little bit about what the architecture looks like for how we actually do things and some of the logic that we've developed that really lets us be modular about taking concepts like the CIMMS tool and applying them to this underlying data lake that we have, which is quite extensive, in a modular way that doesn't disrupt this middle layer, this data storage and aggregation, but adds value and adds functionality in on top of that. So Lauren, Virginia, next slide, please, and Lauren, I'll hand it to you.
Thanks. This slide shows a deeper look at a portion of the Cirrus architecture that enables several interesting use cases related to connected intersections. As an IoT platform, Cirrus connects to and is already managing hundreds of edge devices. The top left of this diagram in that number 1 shaded section shows foundational inputs for device management, including a master list of roadside devices onboarded to Cirrus, which require SNMP and SSH credential management and other key metadata so that Cirrus can access and take actions on the devices. Those inputs then enable Cirrus health monitoring services, which directly interact with devices to collect health data and identify health alerts. And a few examples of those are ping failures, SNMP failures, GPS failures, and other things like CIMMS security certificates that are expired. Our architecture enables us to rapidly iterate and expand on these alerts by updating the logic, doing things like adding new data elements, layering in AI or ML models, and adding new alerts over time. Then, based on the alerts identified, Cirrus can automate actions on devices to resolve issues based on Panasonic's years of experience managing edge hardware. And just like the alert extensibility, we're also able to easily enhance action triggers as new insights and use cases are identified. And through that feature, we can offer 24/7 response to maximize device performance and uptime. Some automated action examples can include things like device reboot, power cycle, and configuration updates if devices are set to the wrong channel or have the wrong forwarding address. In addition to health monitoring, Cirrus has an optimized data pipeline that can ingest any J2735 message type, and that is shown at the top left of the number 2 shaded section in the diagram. Today, we're getting BSM, SRM, SSM, MAP, and SPAT data from the Utah connected intersections. And we've also tested RTCM, TIM, and PSM successfully and are confident in our ability to expand to more message types in the future. And as we just heard, many of these are the data sets that CIMMS uses for the connected intersection monitoring features. And our team at Panasonic is excited about the opportunity we have with partners here today to scale CIMMS across all the
Yeah, I was wondering if it's just me, but I think it is maybe not. Virginia, are you still? Yeah, we lost Lauren.
I'm still here. Lauren seems
All
to be frozen. So
Yeah, fantastic. I'll pick up. I'll pick up and see if I can do justice to her slides. So I think where she dropped off is what she was talking through how we are, as I mentioned at the beginning, we're plugging in the CIMMS logic into this framework where we've separated out the collection of the data from the processing of things like driver warnings and events. And that gives us the opportunity to be modular and add expansion capabilities to plug in those different types of logic that the CIMMS team at WSP has developed. And Lauren, I think you're back, so I will gladly give it back to you.
Yes, I don't know what happened. I think Zoom decided to restart. So I'm not sure what y'all last heard.
One of those days. I think I was finishing up where you were going with this slide, but if you want to talk about what your number 3 was, that would be great.
Will do. Thanks. So number 3 is an example of one use case Cirrus implemented with V2X data that directly provides benefits to drivers by processing BSMs, decoding them, and identifying traffic events based on certain data element triggers. An example of that is Cirrus can detect icy roads from BSMs with traction control engaged, or rain and snow events from wiper activity and temperature. So in addition to the V2X-based traffic events, Cirrus can also integrate with external systems to identify events from weather stations and merge the V2X sourced events and externally sourced events together. Those events are then used to create driver warnings, which differ from the events in the details of the data. So for example, if a traffic event is identified for a vehicle pulled over with hazard lights on, the event might be at a specific point where the vehicle is parked, but the warning may need to be issued up the road from the pulled over vehicle so that drivers approaching are aware of the upcoming hazard. So in that case, the location of the event and the location for issuing the warning are not the same, but the two data events would be related. And those warnings are then used to automatically create TIMMS on the RSUs that are managed by CIRRUS, but we can also send the warnings out to external systems like the situational data exchange. And just like the device health alerts and automated actions, the traffic events and driver warning features are built for extensibility, so we can incorporate new data sources, new logic, new triggers over time. Next slide.
Much better said than my attempt to polish off your slide, so thank you.
Well, thanks for keeping it going. All right, well, now that we've seen a high-level view of CIRRUS architecture for connected intersections, let's go deeper into the data they generate. One of the challenges with scaling CIMMS is the cost of data processing because of the large volumes of V2X data sets. Map messages are really big, and connected intersections send them continuously every second. SPAT is sent continuously at 10 Hertz, and then when vehicles are present, which does happen pretty frequently in the dense enclave deployment in Utah, we also have BSM, SRM, and SSM received at 10 Hertz. So the graph on the left shows peak number of messages ingested per second on a daily basis in Utah just over the last month. And these data volumes are already of the same order of magnitude as large-scale financial transactions and social media. Our data engineering team built CIRRUS with an ELT or extract, load, transform approach, which means we load all the raw data as received, and then we transform it for further processing. So in the case of our V2X data, we have every raw encoded J2735 message for analytics like broadcast rate and message volumes per device. But we only decode, parse, and flatten messages that are unique with the ability to join back to the raw data so that if we needed to know every instance a particular post-process message was seen, we could easily do that analysis as well. Then the graphs on the right show the importance of this optimization by comparing the quantity of raw messages to the quantity of deduplicated, decoded, and expanded messages. Again, there's no data loss with this approach, but the processing methodology is optimized to support analytics and cost-effective data storage. Recent BSM volumes in Utah are shown in the top right graph, with the total number of raw incoming messages in red, and the dark blue has the number of unique deduplicated BSMs. So through Panasonic's data optimization, we're able to reduce downstream processing costs and resources by about half with our deduplication. The difference is even more significant with map data in the bottom right. Maps represent the geometry of an intersection, so they very infrequently change, but they're broadcast every second. So the benefits of deduplication for map are over 99% reduction in volume. We still capture every map timestamp so that we can support CIMMS monitoring use cases, but only unique messages are post-processed for additional analytics. And these are just two examples, but we have solutions for all the J2735 message types we work with to optimize data storage, analysis, and use in downstream applications. Next slide. Okay, CIRRUS has been supporting the Utah deployment for years now, and because we've collected so much data and optimized it for analytics, we're able to do some pretty cool things. In addition to the backend cloud features we've been discussing a lot so far, we also have data visualizations and dashboards that we can iterate on quickly as new user needs or use cases are identified. The graphs shown here display datasets we've been discussing today. So the map on the left shows traffic events identified over the last month, colored by event type. And those events are sourced from both BSMs and road weather information stations across the state. And the dark map is a heat map of hard braking events where the lighter portions have more hard braking events captured. And these are just a few ways we can visualize and analyze events detected by Cirrus traffic event logic. And the dashboard on the right shows some high-level connected intersection performance metrics over the last month in Utah. We've collected data from 52 vehicles making 1.4 million requests at 102 intersections. And we can also see the types of vehicles requesting by role and the number of daily requests by vehicle type. All these visualizations are intended to be interactive in the Cirrus platform, so you can, for example, click on the pie wedge for a certain vehicle type and then filter the rest of the contents for the items that are of most interest. And the dashboards also allow you to view the source query, which can be copied and pasted into our data access tool, so users can get at the raw data behind any of these graphs to tailor analysis and do deep dives on things that are most interesting. And since all of this was built for extensibility, we can easily add and update visualizations like these. So we're excited to leverage that to incorporate analytics and reporting outputs of CIMMS, along with the other intersection and health visualizations already in Cirrus, to deliver a comprehensive picture of the value and performance of Utah's connected intersections. And now I will pass it back to Kel to show some of our other tools.
Yeah, thank you. Next slide. Perfect. Thanks, Virginia. Yeah, so we've talked quite a bit about the kind of the architecture, the structure of how our data comes into Cirrus, and how we're really excited to be able to attach some of the CIMMS logic that WSP has built through their projects. We're really excited about the outcome that that's going to produce. And I'm just going to take a couple more minutes here and just show you briefly a couple of screenshots of some of the actual user-facing products. We kind of have two parts of the platform. You have some of the dashboards and the alerting that Lauren showed. We also have this tool that's a good example of some of the more in-depth tools to actually dig into what's happening in a connected intersection. And so what this tool allows users to do is take a look back at events that have happened at a connected intersection over time, and then hone in on any one of those events that might be of particular interest. And if you jump to the next slide, Virginia, you can actually zoom in and replay a historic event, an interaction of a connected vehicle with a connected intersection. So in this case, maybe we're talking about a transit bus that's getting signal priority along a corridor, and all kinds of things can potentially go wrong with a connected intersection. And so some of it is monitored through the CIMMS tool. And as Lauren said, we're really excited to integrate some of that logic into tools like this to add that functionality to our validation and efficacy work. Some of it might sit outside of that. And so lots of things can happen, right? A connected vehicle that's approaching an intersection, maybe it's a fire truck and they're going around a traffic stop at the intersection, and maybe they're off the map message. And as a result of that, they might not send an SRM. Therefore, they might not make a valid request for priority at the intersection. Of course, if they're not requesting, then they're not going to be granted preemption. And so from a driver perspective, as the operator of that first response vehicle, for example, or a transit bus driver, you might get frustrated and you might complain to the agency or to the vendors who are delivering these solutions. What's happening? Why is it not working? And this tool was built to really answer that question, to let us go back and say, okay, you were there on November 4th of last year. Let's pull that up. You went through at 3 o'clock. Let's replay that instance and let's see what's going on. And using this tool is how we're able to start to find things like understanding that the driver was going around traffic and was maybe off map message and wasn't making the request, for example, or the request came off of the vehicle, the SRM was being broadcast, it was received, but because of business logic rules, maybe the signal controller didn't respond or declined the request. Maybe it was programmed to, have a gap between granted requests, for example, to avoid disruption to traffic. So all kinds of things that can happen. And we want to make sure we understand them, and we either can help set user expectations, or we can dig in and start to fix some of the problems that we're encountering in these intersections and really make sure that they're not only turned on and functional and that we're health monitoring the equipment themselves, but using the CIMMS tool and some of these other things, make sure that they're driving the performance and the efficacy that we've intended for the project. And with that, I think that's our last slide, Virginia. I'll wrap there. I would love to get questions as we get to the end.
Great. Thank you so much, Lauren and Caleb. I really appreciate that great presentation. Again, just a reminder, please enter your questions into the Q&A pod. We'll do our best to answer the questions before we wrap up today, but otherwise if we have something to respond to you afterwards, we can always follow up via email. All right, Blaine, you're up next.
Okay, thank you. And I appreciate everyone joining today. There's a lot of you out there, and it's great to have you with us. I appreciate Frank and Kel and Lauren for all of the background material they've given. My role today is to talk a little bit about sort of the user perspective and how all of this fits in to our system and give you some insight about how you can also use it. This is a snapshot of our V2X deployment in Utah today. We have about 488 roadside units. 406 of those are at state-owned signals, 46 at city-owned signals, 36 at some non-signalized locations. That would be places like Interstate 80, shown in the right-hand center orange line of the map running up from Salt Lake to Park City. And we've equipped about 327 vehicles. Those are transit buses that belong to the Utah Transit Authority, snowplows that belong to us or to Orem City, emergency vehicles that belong to Orem City, and fleet vehicles that belong to both agencies. And we have plans to continue to expand this. We have V2X in about 4 counties now and are continuing to move that forward. Next slide. So our long-term goal with V2X deployment is safety. We've bought into the concept that V2X will reduce crashes, injuries, and fatalities by providing warning to drivers. Now, that requires that the automakers come along and put OBUs in their vehicles eventually. But it's important that we be ready for them and demonstrate that we can provide them the information they need. In the shorter term, since we can't really realize those safety goals today in any kind of volume, our current use cases have a tendency to be a little more sort of mobility related. Transit signal priority, for instance, has allowed us to demonstrate an improvement in transit signal reliability. Giving preemption to our snowplows and emergency vehicles makes them more efficient. It also gets the ice and snow off the road faster. We're gaining vehicle insights. Kel talked about some of that from the vehicles that are connected. We've also deployed examples of curve speed warning and spot weather impact warning, which are safety applications, but not at a large scale today. And variable speed limits and vulnerable road user warnings are things we're currently working on and should have deployed later this year. Virginia, next click. This bullet here, V2I requires participation of the auto manufacturers, is really important. And that's really what sort of triggers kind of the discussion today. It's important that we work with them and make sure that they're comfortable with what we're doing. Next slide. There we go. There's a chicken and egg proposition here. Whether some agencies are waiting for the automakers to start putting OBUs on their vehicles before they start deploying RSUs, we're taking the opposite approach. What the automakers have told us is that they need us to start. We need to be the chicken that lays the egg. They need us to deploy a significant base of roadside units. If you read the ITS America National V2X deployment plan that was talked about by Frank earlier on, it states in there that the OEM implementation is anticipated to be about 3 years after the FCC second report and order. They need that certainty before they can move ahead. We hope to see that second report and order maybe late this year. I'm not quite sure. I know it's being worked on. And so there's a lot of anticipation here and a lot of activity forthcoming, but we need to create this base so that they can justify building OBUs into their cars. It's also important that in a safety application that the OEMs trust the messages that we send. Those have to be accurate, consistent, reliable, and secure. There's no way that the automaker is going to take our messages and make a safety critical decision in the vehicle if they don't trust our data. So this validation testing and monitoring that Frank talked about in some detail really is based on this concept that for safety applications, these messages really need to be trusted. Virginia, if you click here, this is This is where this really comes into play. We must verify and demonstrate that our messages are reliable. Next slide. So there are 2 steps to this, and Frank talked about this in some detail, so I won't too much. The initial verification is that the RSU broadcasts are acceptable, and we are working with the OEMs and SCMS manager, following the CTI 4501 guide, working closely with that committee on its next revision, following and helping to advance the Connected Intersections guidance document that was referred to. In Utah, we have some SMART grant funding to build some of these tools and processes that we hope to share with deployers around the country to be able to do this initial verification. I will tell you that this verification is not a trivial exercise. I went into this believing that our broadcasts were in pretty darn good shape and discovered a lot of little problems that we've had to deal with. So we're learning a lot in this process and hoping to share it with everyone else. Then there comes the CIMMS process, where after we initially verify that the intersection is operating correctly and broadcasting accurate messages, that it continues to do so. And so that's important. Next slide. So our initial work on this initial verification process involved 6 intersections near Park City, in the blue box on sort of the lower right part of our map, 1 intersection in American Fork, and 1 intersection in Orem. These were particularly selected because they have different signal controllers. We wanted to make sure that different instances of our RSU deployments would all operate the same. Next click. As we moved into CIMMS work, we picked 3 intersections in Orem, one of which was coincident with the initial verification intersection. And then we've added 2 intersections near Park City, which is part of that same initial verification corridor. Next click. As has been discussed, there are also 3 intersections in Anthem, and there are a number of intersections being tested in Denver, sort of independent of our project, if you will, but being done by part of the WSP team there. So there's a lot of work on this to try to advance CIMMS and make it more robust and make it more useful. Next slide. So if I can emphasize the importance of verification and the CIMMS monitoring process, if the OEMs can't trust our data, they won't rely on it for life-saving crash avoidance applications. So we won't get the safety benefits we need in these low latency, safety critical applications if we can't get the data to be in a condition where it's trusted. So it's essential that we develop these tools and that we use them, that we make them practical and functional for those of us in the IO community. We need OEM engagement during this process, and we have worked really hard to have that so that we are on the same path. We know we're moving in the same direction. We need uniform testing tools and policies so that we can be interoperable nationwide. These applications need to operate across borders. And so it's important that we have consistent policies, and we're working on that. I believe that CIMMS will be a useful diagnostics tools for intersections beyond just the data trust element. We find after we install an RSU that someone else in the agency comes along and makes a striping modification or a small construction modification. They don't tell us that. We're not looking at these intersections every day. This is a great tool that will help us just sort of monitor our intersections and that the RSUs are doing the right thing beyond what we're trying to achieve with trust with the OEMs. Next slide. So our next steps in Utah and as a team are to refine these tools and processes. This includes modification of some of our deployments. We've found, for instance, that we've had to modify our map messages to comply more completely with CTI 4501. Little details that weren't there before. And we need to work together to develop the policies and processes and tools and make them available for everyone. We plan in Utah to expand CIMMS to more intersections, and we've already done that with 2 intersections in Park City. One of the hurdles we have today, and Lauren talked about this, is the data storage and cloud costs. They are still more expensive than is practical if I were to put CIMMS at 488 intersections or 460 intersections. So we're working to reduce those data volumes by parsing the data down and integrating that into Cirrus, where we've got redundant data already, and reduce that redundancy will hopefully get us down to a functional system there. So we will incrementally expand along the Park City corridor and then into other places, with the ultimate goal being signalized intersections all over the country. So with that, next steps, let me just give you a summary of, I think, the key points from today's webinar. Accelerating V2X deployment will save lives and improve transportation. And in order to do that, we need to work together with the IOOs and the OEMs to make this happen. We both have a part to play. We both have to step up and, frankly, take a little risk to move this forward. Integrating technology and connectivity into a Vision Zero approach requires interoperable connectivity. And these uniform testing tools facilitate that national interoperability. And as we work together to develop trust in our data, we can hopefully get there. The V2X messages must be accurate, consistent, reliable, and secure. As Frank said, compliance with J2735 by itself is not enough as we get into individual applications. And we as deployers will need to tweak and adjust our systems to make sure that happens. CIMMS will be a valuable tool, monitoring tool for all of us. And we're hoping it can be integrated fully into V2X architecture everywhere. So with that, I will turn it back to Virginia and thank everybody for your participation today.
Thank you, Blaine. Thank you for that great presentation and the wrap up on why today's webinar is just so important in order to advance connected intersections and VDOCs within the connected interspace world. We do have a few questions, so let's see. I know that some of the questions have been answered live, so that's great. I guess one question I think we'll just kick this off with is, how have OEMs in the auto industry been involved with this process so far? We'll just maybe start there. Does anyone want to, I guess if we could have everybody come on camera and
so I can jump in there a little bit. So first of all, these standards efforts, CTI 4501 in particular, is a group that's made up of people across the industry. IOOs, OEMs, equipment suppliers, vendors are all in there developing the standards. As we have worked on in Utah on verification testing and developing tools, and as we work with the CTIC committees, we have engaged automakers in that effort. They're part of our SMART grant team as we're developing these things. So we're sharing the workload with them. They're helping us and we're helping them.
Yeah, and I'd add to that, Blaine, that I think some of the work that we're trying to accomplish with things, validation tools like CIMMS, is to demonstrate the effectiveness and the usability, if you will, of some of these connected intersection applications, in part to help solve the kind of chicken and egg problem between IOOs and the automakers, where both sides maybe are looking for someone else to start. I think you've been an advocate, Blaine, for let's start, and I think CIMMS helps to advance that.
Yeah, I think CIMMS really is kind of an outgrowth of the concern that the OEMs have had about consistency of the data, right? With, CIMMS monitoring the data, it, goes much farther to reliability of the data.
That makes sense. And then another question. So how does this relate to the cellular-based connectivity and the connected services that are really gaining popularity in light vehicles and other vehicles right now?
I think I answered part of that one in the chat, so maybe I'll kick off real quick there. I think from Panasonic's perspective, there are different types of connectivity that are ideal for different types of applications. And so you need the very real-time OBU and RSU 5.9 based capability to do some of the real-time safety functionality. There are some other things that you potentially could use other hardware endpoints for. And what we're working through right now from a product perspective is trying to understand which devices work best for which different types of applications, and where can we support and potentially integrate or allow for interoperability between some of those different endpoints. So we are looking at how what's the best type of communication platform or mechanism for different applications and trying to use the right one.
Yeah, and I think the 5.9 is really critical when we're talking vehicle to vehicle communications, you know, for safety applications. You know, as Khalid said, we, you know, they're traditional cellular is, you know, is sufficient for some things, but, you know, I think vehicle to vehicle, it's not going to support latency. Also, you know, broadcasting stat and map. So map is map is one of those things that can be broadcast through other means. Sorry, I turned my camera on. You know, but SPAT really is real. It's real time. So, you know, as the controller is going through its timing changes, you know, that has to be reflected over the air. I know there is efforts underway to kind of assess the potential for broadcasting SPAT over traditional cellular. You know, but I think that's still kind of in a prototype investigation type stage. So.
All right, thanks everybody. I'm going to go for one more question. I'll do a round. We'll hit on everybody. If you can give a quick blurb, your thoughts on what do you recommend to advance CIMMS deployments? So what is maybe one thing that our audience can do to help advance a CIMMS deployment in their area or with the things that they're working on? Frank, you're on screen, or for me, so how about I'll start with you.
Yeah, so as I mentioned, you know, it has been mentioned, right? CIMMS is open source. You can download. There are 3 separate packages on GitHub, I believe it's JPO GitHub, that you can download. I'm happy to provide those links, you know, after the meeting. And right now, CIMMS is cloud-based, but it doesn't have to be. It could be run at the intersection, but I think it's a little bit easier right now to manage if it's cloud-based or at least TMC-based. So, you know, there are documents available through as well through the pooled fund study. So I guess I would encourage folks to look at those, and again, we can provide links to those, you know, to help prepare your sites for deploying CIMMS.
Okay, thanks, Frank. Lauren, I'll go to you next. What's one thing from your perspective that folks can do to help deployment?
Yeah, I think just getting started, even just one intersection is a great starting point. We've got instructions on how to set up the network, how to point the devices, and would be happy to help anybody that is trying to get something off the ground.
Great, thanks, Lauren. Kale, what's one thing for your perspective?
I mean, I'm responsible for the sales team here at Cirrus, so I'm just going to make the direct pitch. Cirrus is a great way to get started. We're integrating some of these tools and building them into the product. I think that's a great place to start, and we can talk about what that looks like.
All right, thanks. And Blaine.
So I think I will reflect something that Lauren said. You know, you can't use CIMMS unless you've got some RSUs installed. And the place to start is to install a few RSUs. Pick a location, upgrade your signal controllers if you need to, rely on the connected vehicle pooled fund study, connected intersections document that tells you how to move forward, and install a few RSUs. You won't get it right the first time. So take a little risk, expect a little work. It's worth it in the long run, but you have to start someplace. Start small, experience this, and get ready for what's coming.
Yeah. All right, thank you for that, Blaine. And again, please join me in thanking our panel for taking the time today to share their experience and their thoughts working with connected intersections and advancing CIMMS, and really to advance V2X technologies at scale. So thank you all for being here today. And Dorina, back to you to wrap this up.
Sure. Thank you, everyone. Continue to look out on the ITS America website for our next webinar, which is coming up on the 17th. All right. Take care, everyone.